All right, we're talking about projectile motion, and this is chapter 5. So we're talking about a projectile, first of all, is just anything that moves through space acted only upon by gravity, and typically Earth's gravity, since that's where we're at. And it can have any given height and can move toward the ground in any arc, and they all follow the same set of rules as we do this. So let's kind of just quickly go over these. So here's our rules. First of all, projectiles always maintain a constant horizontal velocity, and that's important. Use that a lot. You use that to figure out, if it's got to go this far, it's going to take that long to get there, and then I can figure out how high or something went. They always experience constant vertical acceleration, that's gravity, 10 meters per second squared. The two different components are completely independent. Horizontal and vertical are independent. And for a projectile beginning and ending at the same height, the time it takes to reach the highest point and the time it takes to fall from that point back to the original position are the same. In other words, it takes the same amount of time to go up as it does to go down. And objects dropped from a moving vehicle have the same velocity as the moving vehicle. So if you were in an airplane, you have some velocity when you jump out. You have that velocity. You have the airplane as you jump out in order to do that. In order to solve these exercises, you have to consider horizontal and the vertical separately. It's two problems. There's typically two different things you do when we're working with projectile motion. The nice thing is we're using the same equations we did, but you just have to do two different ones. And the key is trying to figure out how to solve the one by using the other one, I guess is what it is. Now, they're going to say they're going to simplify everything. We're not going to talk about initial velocity here. And I don't know what happened on here, but these should all have a 1/2 in here. So in your book, it's fine. But for some reason actually on the PDF, it probably isn't fine. So, but that should be 1/2. So 1/2 GT squared is my formula for that distance. All right, let's work through a few examples. In her physics lab, Melanie rolls a 10-gram marble down a ramp off the table with the horizontal velocity of 1.2 meters per second. So there we go, 1.2 meters per second. The marble falls in a cup, placed 0.51 meters from the table's edge. How high is the table? So really all we need to know is how far it was to here, and we can figure out this distance. That's what we're telling you. Okay. We don't really care about the mass. Mass of the marble is irrelevant because everything falls at the same rate if we neglect air resistance. So here's what we got to do. We got to figure out our height. That's what we're trying to do. This is a distance term. And so if we knew, now we can use, like we've got this formula, distance equals 1/2 AT squared, and we know that, it's 1/2 times 10, but we don't know T. So if we could figure out T, we could figure out this distance. Well, we can figure out T on the horizontal distance. So we can do that. So we figure out T doing it horizontally, and then we use that in here to figure out the vertical distance in this example. So, right now what we've got is we have the distance of 0.51 meters, and we know a velocity, 1.2 meters per second. Well, that's a pretty easy problem. We can figure out, velocity is distance divided by time, and we're looking for time, so time is going to be distance divided by velocity. So it's going to be 0.51 divided by 1.2, or 0.43 seconds. So the time it took for that ball to fall was 0.43 seconds, and we know that because it took it that long to go 0.51 meters for it to hit the table. So now we know we take this 0.41, or 0.43, plug it in, and we should get our final answer by doing that. So plug into 0.43, square it, take it times 10, take times 1/2, and you end up with 0.92 meters. So that table was 0.92 meters above the floor. So do you see how you work two different problems? You work the horizontal problem and get the time, then you take the time, plug it into the vertical problem to get the distance. So that's usually how these problems work. There's usually those two things that you've got to take care of when you're doing these problems. All right, let's do another one. Oh, come on. Bert is standing on a ladder picking apples in his grandfather's orchard. As he pulls each apple off the tree, he tosses it into a basket that sits on the ground 3 meters below at a horizontal distance of 2 meters from Bert. How fast must Bert throw the apples horizontally in order for them to land in the basket? Hope he's not picking my apples because I don't like mine bruised. All right, so let's figure out, first of all, before we can figure out the horizontal component, we have to figure out the time. In this one, it's easiest to figure out the time by the fact that we know he is 3 meters above the basket. So I can figure out time, and we've got that formula, right here. We've got time is equal to the square root of 2d over g. And we know our distance is 3. We know our g is 10. And we know 2, still do. Square root of all that, 0.77 seconds. So for the apple to fall 3 meters, it's going to take 0.77 seconds. Okay. Now we take that time and we plug it into here. Oops, not that equation. We plug it in somewhere else. We take that time and we plug it in down here. Okay. So we've got we want to figure out what our velocity has to be. And we know our distance. All right, so get rid of that one. We don't want to go there. That's the old problem. We want to go down here, and we want to figure out our velocity. So, velocity is distance divided by time. The distance from here says it is 2 meters. 2 meters. I don't have enough space for all this. Time, we calculated 0.77 seconds. So my velocity is going to be 2.6 meters per second. All right, let's work number 8. Emmanuel Zucchini, the famous human cannonball, was fired out of a cannon with a speed of 24 meters per second at an angle of 40 degrees to the horizontal. If he landed in a net 56.6 meters away at the same height from which he was fired, how long was he in the air? So, one of the key things is always get your diagram. So he's fired out of the cannon, it is from across here, it is going to be 56.6 meters. The angle, if we just kind of do this in here, the angle is going to be 40 degrees. And he's fired with a speed of 24 meters per second. Now, one of the key things on the test, or anytime we do these, is to write your diagram, start your work, show what you're given, figure out what you want to have. What are you trying to find? All right. So here's what it says. Because he was in the air for the same amount of time vertically that he was horizontally, you can find his horizontal time, and this will be the answer. So first we need to figure out the horizontal velocity component. In other words, what we're saying is we don't even care how long it took him to go up and how long it took him to go down. We just care how long it took him to go across because those are the same thing. They're exactly the same. So let's make my triangle. Let's break this down now. 24.0, 40 degrees. We don't know what that is. Don't really care. Okay. We know that 24 meters per second. So we can figure out his horizontal velocity from that. That will be this right here. So in order to figure out horizontal velocity, we're going to do cosine 40 degrees equals x over 24. So punch that in, and you're going to get, I'm going to just cheat and kind of scroll down the screen here. All right, so we punch it in, and we get 18.4 meters per second. So that's his speed. Well, we know this is how far he went. That's the distance. This is the speed or the velocity, and we know that velocity is distance divided by time. Okay, so we can solve for time in this particular formula. So solve for time, we're going to get distance divided by velocity. Distance was 56.6 meters. The velocity was 18.4 meters per second. And when you divide that out, you get 3.08 seconds. So that's his time to go up and down. It's also his time to go across. They're the same thing. All right, one last one. On May 20, 1999, 37-year-old Robbie Knievel, son of famed daredevil Evel Knievel, successfully jumped 69.5 meters over Grand Canyon Gorge, not George. Assuming that he started and landed at the same level and was airborne for 3.66 seconds, what height from his starting point did this daredevil achieve? So, we're talking about how high did he get, here. And we're saying that he's in the air for 3.66 seconds. Well, remember this. When he's in the air, half his time is spent going up, half his time is spent coming down. So if he's in the air for 3.66 seconds, he's only falling down for half that, 1.83 seconds. Going up for 1.83 seconds. We can figure out that distance. So the distance is 1/2 AT squared, 1/2 GT squared, 1/2 10 times 1.83 squared equals 16.7 meters. There you have it. You are now ready to go on and do more practice problems.